Welcome, honors students. Today's virtual lesson is going to wrap up 14.2, and it is the combined gas law. We have studied over the last three virtual lessons the three primary gas laws, being Boyles Law, Charles Law, and Gay-Lussac's Law. Now we're going to actually learn how those particular gas laws were derived. It's actually from the combined gas law. So, key concept here. How are the pressure, volume, and temperature of a gas related? One really important keynote I noticed going through a lot of the work, the temperature cannot be in Celsius. It must be in the Kelvin temperature. So if you're in Celsius and you're degrees Celsius, you have to add 273 to get Kelvins. So please make sure you make a very important note of that. You have to be in Kelvin or the gas laws do not work out properly. All right, so let's get started on this. So here is the combined gas law. And once again, it is a combination of the three laws that we learned. So pressure 1, volume 1 divided by temperature 1 equals pressure 2, volume 2, temperature 2. So we are going to look at this particular formula today and look at some example problems. One thing let me stress, please, on this particular one, there is a lot of variables to write down. You have pressure, volume, temperature, initial and final, solving for one of those variables. So this is the combined gas law. It is on the worksheet that I had given you to print. It's actually a formula sheet. It's on Moodle for you to print and utilize that. It's there for you. You can use it when we have the assessment on this particular section as well. So, key concept. When only the amount of gas, so the only thing that is constant is N, and that is moles. All the others are variable. So that means there's changes in them, and that's why all three variables are given to you. This describes the relationship from pressure, volume, and temperature. So we learned previously in these other lessons that if you talk about pressure to volume, it is an inverse, and if you have a scale, a graph, it's going to look something like that. Then we looked at volume to temperature, and we learned that that's a straight line. And then we looked at pressure to temperature, and that also is a straight line. That's the relationship. Now you don't have a straight line or a curved line. This one here is three variables that are changing, so you don't have it on a graph, but it's important to know the graph for those particular ones I just went through. So let's look at how they derived, at least Boyles. We'll look at Boyles Law. How did they derive PV equals PV, initial versus final? So let's look at here. So when you look down at the bottom, it says, suppose you hold the temperature constant. So don't let this confuse you here. This did have temperature 1 on the bottom. So this is P1 V1 over T1 equals P2 V2 over T2. And just disregard the T1 on this side here, right there, because that came from here. How did they get it over there? Well, they multiplied both sides by T1, and then it canceled from here. That's how it got over there. So when you look at T1 and T2, if you hold the temperature constant, say it was 298 Kelvin, if you have 298 Kelvin here, and you have T2 at 298 Kelvin, they both cancel. So even without a unit, all they're doing is canceling off like terms. That's how temperatures canceled off, and you get P1 V1 equals P2 V2. And that's exactly how they did all of the gas law formulas. And once again, it just goes into a little bit more detail here about Boyles Law. And that's how you get P1 V1 equals P2 V2. I just explained that, canceling them off. So don't be afraid of the formulas. Learn to work with formulas And I'm trying to show you that when we do each one of these example problems. So it's a similar process if you look at Charles' law or Gay-Lussac's law. If you hold one thing constant, you can cancel it from both sides, and you eliminated that variable. So let's look at the combined gas law. So here's an example let's look at. The volume of a gas-filled balloon is 30 liters at 313 Kelvin and 153 kilopascals of pressure. What would the volume be at standard temperature and pressure? Well, standard temperature of a gas is 0 degrees Celsius, which is 273 Kelvin. And then we would have our standard pressure is 1 atmosphere, which is 101.3 kilopascals. So let's look at what they've written down here. And look at that's what they've done here. So look at the list. The list is a little extensive, so it does take a little bit of time to write down all these variables. And what are you solving for here? It's actually asking you for your volume secondary. So they've written down their formula. One of the ways I'm going to show you this is simply break it up and cross multiply. So when I say cross multiply, it's this right here. So you could easily rewrite this formula. It makes it very simple, actually. You go P1 V1 T2 equals P2 V2 T1. And if I'm solving for my secondary volume, if I back up, that's what it's asking for right there. I simply have to divide both sides by P2 T1, P2 T1, and they are crossed off on both sides. So that isolated my volume secondary. And when we turn the slide over, you're going to see that's exactly what they've done. They have the exact same formula that I have there, and that's how they've done it. I think that the way they show it is maybe a little bit confusing. That's why I wanted to show it step by step. Once you've got that, all you have to do is plug in your numbers. And that's what they do here. They cancel off their units. Please make sure you're in Kelvin. That's very important. And now they come up with, once they plug in the calculator, 39.5 liters. Does it make sense? Yes, it does make sense. So here's a checkpoint question. You might want to pause the video and try this on your own, and then we're going to come back and do it. All right. Which of the following equations could be used to correctly calculate the final temperature of a gas? So that is looking for T2. So remember our formula. So we have P1 V1 T1 equals P2 V2 T2. And I told you just cross multiply. So I'm going to have P1 V1 T2 equals P2 V2 T1. And I want to get my T2. So I'm going to divide both sides by P1 and V1. And I can cancel it off on this side. So which one of these looks that way? So we all have T2 here. When we look at this here, should be B. It has V1, P1 on the bottom, V2, P2, and T1 on the top. Check. So that is correct. That's the one. That's how you utilize the formula. Just change it around, makes it very simple, isolate it, and plug in your numbers. Let's do an example. So here we have a quick example to look at. A gas at 155 kilopascals and 25 degrees Celsius has an initial volume of 1 liter. The pressure of the gas increases to 605 kilopascals as the temperature is raised to 125 degrees Celsius. What is the new volume? One of the quickest ways to know you're dealing with a combined gas law problem is look at all the variables. You notice nothing is said to be held constant. So with that being said, let's write down all our variables. So to begin with, I like to write my equation. So I'm going to go P1 V1 T1 equals P2 V2 and T2. So now I'm going to come over here and write down everything. P1, and I like to be very orderly with my variables, P1, V1, T1, P2, V2, T2. And then I'm just going to come up here and fill them all in. So pressure 1, it says 155 kilopascals. So 155 kilopascals. And please remember, you got to look at your significant figures. All right, so next thing I have here is 25 degrees Celsius. So I have, that's my temperature 1, 25 degrees Celsius plus 273 equals. And this is going to be 295 Kelvin. So I change it right away. That way I do not forget. My volume, it says, is 1.00 liters. It says my secondary pressure is very high. So I went up to 605 kilopascals, and the temperature went up to 125 degrees Celsius plus 273. So I'm just going to plug that right in. So 273 plus 125, and that gives me 398 Kelvin. So 398 Kelvin. And the only thing that's left here is my new volume, and that's going to be here in liters. Now, knowing that's what I'm going to solve for, I'm going to cross multiply here. So I'm going to go P1 V1 T2 equals P2 V2 T1. I'm solving for volume 2. So I'm going to isolate volume 2 and put P2 and T1 on the bottom, and that crosses them off. So now I can just simply plug in. So my pressure 1 is 155 kilopascals. My volume 1 is 1.00 liters. My temperature 2 is 398 Kelvin, divided by my pressure 2 is 605 kilopascals, and my temperature 1 is 295 Kelvin. So my Kelvins cancel, my kilopascals cancel, and that leaves me my liters, which is what I'm solving for. And when I look at what I need to be at, I have 3 significant figures. I've got to stay at 3 significant figures. So I have 155 times 1.00 times 398. I'm going to divide that by 605 times 295. All right, so my volume 2, 3 sig figs, 0.346 liters. So that is my new volume. So I've fallen in my volumes from 1 liter down to 0.346. Okay, so now let's look at the next problem. So here it says 5 liters air sample has a pressure of 107 kilopascals at -50 degrees Celsius. If the temperature is raised to 102 degrees Celsius and the volume is expanded to 7 liters, what will the new pressure be? So once again, I see these variables, it alerts me of what I'm going to be using. So I have P1, V1, T1, P2, V2, T2. And now I write down all my formulas. So P1, V1, T1, P2, V2, T2. And I'm very regimented about how I do these things. You've noticed that in class, and hopefully you're noticing that in these virtual lessons. So my pressure 1 is 107 kilopascals. My volume is 5.00 liters. My temperature is negative 50 degrees Celsius plus 273. So that is going to leave me with 223 Kelvin. Then my pressure 2 is what I'm solving for here. So I'm going to put blank kilopascals. My volume 2, it expanded. It went to 7.00 liters. And my temperature was raised to 102 degrees Celsius plus 273. And that is going to be 375 Kelvin. So now I'm prepared to manipulate my formula to isolate my variable. So once again, I cross multiply right away. So I go P1 V1 T2 equals P2 V2 T1. I'm solving for P2, so I'm going to get rid of V2 and T1 and cross them off. And now I'm ready to plug in my information. So P1, so I have 107 kilopascals. My volume 1 is 5.00 liters. My temperature 2 is 375 Kelvin divided by my volume 2 is 7.00 liters. And my temperature 1 is 223 Kelvin. So now I can cancel off my Kelvin, cancel off my liters, and that gives me my kilopascals, which is what I'm solving for. So my pressure final is going to equal, so I get my calculator, 107 times 5.00 times 375 divided by 7 times 223. And I have to be at 3 significant figures again. So my answer comes out to 128.5. So that means it should be 129 kilopascals. So my pressure went up slightly. So it went up to 129 kilopascals. And I'm in my 3 significant figures. So those are 2 example problems. You have a worksheet coming up due on Friday that has a few examples for you to try. So ladies and gentlemen, that wraps up this entire section of 14.2. So we talked about a lot of key concepts. We looked at Boyles Law, Charles Law, Gay-Lussac's Law, combined gas law. It's all there on the formula sheet for you. You don't have to necessarily memorize them. You just have to know how to use them because they are on the formula sheet. So you have definitions. Remember, they all are associated with the definition as well. And ladies and gentlemen, that is the end of 14.2. So I will have a new virtual lesson for you on Friday, and it will be beginning the ideal gas law. So thank you for watching. Go in peace.